So can you hear me?
Yes, ma'am.
Perfect. We'll start in 4 minutes. So Mia, can you see the polls? There must be 4 of them. I can't see them.
Let me check. There are 4.
Perfect.
And that's in start now.
Okay. So release them when the polls come up.
Okay.
Very good. All right, folks, let's begin. So we're going to continue our series of lectures on convolutional neural networks. And this is the last lecture in the series. So here's what we're going to do. We're going to have a quick recap. We're going to finalize some of the topics in backpropagation through a CNN that we did not touch upon in the previous class. We're also going to look at modifications to the basic shift invariance property, namely scaling, rotation, and deformation invariance. And we'll look at segmentation and localization and some success stories. And time permitting, we'll look at some so-called advanced architectures, which are very far from advanced today, but were some of the earliest advances that were proposed to CNNs. So here is the story so far. Shift invariant pattern classification tasks, such as does this picture contain a cat, or does this recording include hello, are best performing by scanning for the target pattern using convolutional neural networks or time delay neural networks. These are shared parameter models that can be trained with variations of backpropagation. And so here's how backpropagation was performed. For each training data, we first pass the data instance through the model to get an output. You'd compute the divergence between the output of the model and the desired output. And then you'd propagate gradients backward using conventional backpropagation rules until you came to the first layer of the MLP that followed the CNN. Then the gradients with respect to the input of this MLP would be folded back to get gradients for the derivatives for all of the channels of the final layer of the CNN. And from there on, we would use the backpropagation rules that we've seen earlier in the last class to propagate derivatives further backward. And these backpropagation rules must consider the shared computation and convolutional layers and the somewhat funky computation of the pooling layers. So here's what we needed. At each layer, if this was a convolutional layer, given the derivatives for the output activation maps YL, where L represents the layer, we would first need to figure out how to compute the derivatives with respect to the affine map ZL. And then given the derivative for the affine maps ZL, we would have to compute the derivatives with respect to YL minus 1, which is the output of the output maps of the previous layer, and also the derivatives with respect to WL, which are the filters that were applied to YL minus 1 to give us ZL. For the pooling layers, given an output, the derivatives with respect to an output YL, we had to compute the derivatives with respect to the input Y of L minus 1 to the pooling layer. Now, for the first one, the derivatives for the convolutional layers, given the derivatives for the output activation maps, how would we compute the derivatives with respect to the affine map? This was easy. Here's how we did this. To get the activation map from the affine map, we applied an activation function pointwise to all of the elements in the affine map. And this gave us the activations in the activation map. So YLMXY, which is the activation at the XYth position of the mth channel of the Lth layer, was obtained by applying the activation F to the XYth element of the mth channel of the Lth layer, mth affine channel of the Lth layer. So then just using standard derivative chain rules, this meant that the derivative of the divergence with respect to ZLMXY, which is the affine term, was simply the derivative of the divergence with respect to Y LMXY times the derivative of the activation function itself computed at that Z value. So this was easy. This tells us how to compute, how to propagate derivatives for the activation maps backward to the affine maps. So this first derivative operation is defined. The second one was now how to compute the derivatives with respect to the input to the convolution, and also how to compute the derivatives with respect to the filters. Do you remember how these operations were performed? Anyone? How were these operations performed? Any answers? Hello?
Flipping the convolutional matrix and going back on the.
Can you repeat that, please?
We were flipping the convolution matrix and then multiplying that with convoluting that on the DLDZ that we got from the next layer and then going to the previous.
There are two different derivatives we are speaking of. One is the derivative with respect to Y, The other is the derivative with respect to the filters, correct? So how did we compute the derivatives with respect to the filters? These guys. Anyone remember? Anyone? Convolve y with dldz to give it to get w, correct element. And to get the derivative with respect to y, what did we do? Anybody? Okay. So convolve flipped the transpose w with dldz. So that's exactly what we did. Let's look at the first one. If I want to compute the derivative of the divergence with respect to the mth input channel, then I would consider the mth channel of all of the filters. This mth channel is now going to be transposed, which is flipped left to right, top to bottom. The output derivative maps, the derivative maps for all of the affine outputs are zero padded, and then these transpose filters are convolved with the zero padded derivative maps for the affine layer, and that gave us the derivative for the input channel. Do you guys remember this? There's a single yes. What about the rest of you guys? Right. And that's very easy to do, right? Once you see what is happened, what is done over here. So also, when you wanted to compute the derivative for the filters, to compute the derivative for the nth filter, we convolved the derivative map for the nth output affine channel with all of the input channels. And that gave us the derivatives for all of the channels of the filter. Do you remember this? Right. So easy, right? And so we've seen how we can back propagate derivatives over here, back to here, and from here back to here, as well as compute derivatives for all of the filters. Now the next operation was, so this term is dealt with. The next operation is figuring out how to compute derivatives for the pooling layers. And we considered two kinds of pooling, max pooling and mean pooling. How did we compute derivatives for the max pooling? Anybody remember? How did we back propagate derivatives for max pooling? Anyone? Someone. I
By
have a few seconds.
storing which index the max came from and then sending it back to the max one and keeping 0 for the others.
Exactly. So here, max pooling pools groups of values to reduce jitter sensitivity, right? And when you perform max pooling, basically you're just computing the max value over. And that's what we do through the scan. When we propagated derivatives backward, we know that only the max element was copied over. So the rest of them had no influence on the output, which means that the derivatives of the divergence with respect to these guys must be 0 because they do not influence the output. And the derivative with respect to the element that was copied over, this element was copied over exactly. So the derivative out here can be copied back exactly over here as well. So this was the back propagation for the max pooling layer. Everybody remember this? How did we do the back propagation for the mean pooling?
The mean pooling is for each element in the kernels, we divide it by its kernel size.
Fantastic, right? So this is okay, this was the max pooling. For mean pooling, we computed the mean of all the elements in the window to obtain the output going forward. So when we perform back propagation, we just redistributed this derivative uniformly over all of the elements within the window. So if this window was size 4, it has 4 elements, then 1/4 of this derivative went into each of these locations. And you actually do a plus equals because we know that and any element may occur in multiple adjacent overlapping windows. Now, does this operation look like something to you guys? What does this operation look like? Anyone? What does this operation look like?
Upsampling.
Upsampling? Not really. What happens is, so this was the mean operation going forward. This is what we did. This is the pseudocode for the back propagation for mean pooling. But then really, what we do for mean pooling is since each element is being spread across 4 elements over here. So this is like having a kernel of 4 1/4s. And you're zero padding the derivative map, and then you're convolving it with this kernel. And that gives you the derivative map for the mean pooling, back propagated derivative map for the mean pooling. That makes sense? Okay. So mean pooling is different from max pooling. You can't think of max pooling, back propagation rules in max pooling as convolution because you're picking an element. For mean pooling, it's simpler still. You can just back propagate using convolution itself, except the convolution is now performed channel-wise. Okay? Any questions? Any questions? No. Okay. So we've handled all of these. But there were a couple more operations for which we have not considered back propagation rules. What were those? Anyone? What were the operations for which we haven't considered back propagation rules? Does anyone want to volunteer? Okay, let me remind you. But before that, here's a poll. Mia, can you release this poll? Yeah. Thank you, Tom. Absolutely. All right, 5 seconds and we'll close the poll. Thanks. Mia, can you close the poll? Yeah. All right. Here's what we got, right? So for the first question, what is the answer? When back propagating from max pooling layer, derivatives from the pooling outputs propagate only to the position of the largest? True. For the second one, also true. Beautiful. You guys got it, right? So let us continue. Both of these are true. Now, the next operation we must consider is upsampling and downsampling. Upsampling layers and downsampling layers increase or decrease the size of the map. And we also said that upsampling must always be followed by a convolution, otherwise it doesn't make sense. So upsampling followed by convolution can or is often termed as convolution with a fractional stride. And Aryan, yes. And similarly, convolution is always followed by, downsampling always follows convolution or pooling. So convolution followed by downsampling can be viewed as convolution with a stride greater than 1. And similarly, pooling followed by downsampling can be viewed as pooling with a stride greater than 1. But then, how do we propagate derivatives through upsampling and downsampling layers? Now, here's what happens in downsampling. You start off with this large map, right? Then all of these blacked out entries are essentially ignored. In other words, you can think of them as being zero because we are not going to use them. And only the remaining entries are copied over when we are downsampling. This makes sense? As the downsampling operation, guys? Right. Okay. So, do any of these blacked out elements influence the output? So, what do you think the derivative of the divergence with respect to those blacked out elements will be? 0, right? On the other hand, what about this guy here, this cyan element here? Does that influence the output? What do you think the derivative of the divergence with respect to this element will be? It's going to be the same as the derivative of the divergence with respect to this guy, correct? Because it's just copied over for downsampling. Right? Yes or no? And so, here's what we're going to get. When I want to, first thing, no, Evgeny, you just for downsampling, you just literally dump things, you drop stuff, right? It's like, performing the convolution with a strike. So, first thing, we know that downsampling, the input to the downsampling is some size. Downsampling is some operation, and the output of downsampling is some size, okay? But then when I propagate the divergence, derivative of the divergence back through the downsampling layer, what will the size of the derivative be once it is propagated backwards through the downsampling layer? What will the size be compared to the size of the input to the downsampling? Anyone? It's going to be the same as the size as the input, right? If some variable x influences the divergence, the derivative of the divergence with respect to x is going to be the same size as x. So the first thing we will do is to allocate a derivative map the same size as the input. You set everything to 0 within this map. Then you want to propagate these derivatives back to into this map. And all you have to do, right? So you want to allocate a map the size of the input that was downsampled. So you have to retain the size of the map, or can be derived from the known size of the previous outcomes of the previous layers. And then we know only these grayed elements are going to have non-zero derivatives. The blacked out elements never influence the output. So what will their derivatives be? 0, right? So I can just stick zeros over here. Right? What about the rest of the elements? What do I do? What would I do for the rest of the elements? Just copy them over, like so. Beautiful, right? So back propagating through a downsampling layer is really trivial, is it not? What is this operation? This back propagation through a downsampling layer. What is this operation? It's upsampling. So back propagation through a downsampling layer is upsampling. Fantastic. Now we just copy these things over. So simple. Now, if I write code for it, basically I allocate some variable, a derivative map the size of the input, and then copy the appropriate elements over. Now, what about upsampling? What did we do in upsampling? Anybody remember? What did we do in upsampling? We just inserted rows and columns of zeros, correct? They're not empty spaces, they're spaces of zeros. Now tell me, consider this element over here. Is there any element of the input which influences this value, this gray box? Is there anything in the input that influences the gray box? None, right? So is there anything from the gray box that can be back propagated? because that was not influenced by anything in the input, right? So what do you think I will be doing when I'm back propagating the derivatives from the output of upsampling to the input? Downsampling, beautiful. I just throw all of those guys out. So I'm going to, when I back propagate initially, I'll have derivatives all over here. But only these guys were actually obtained from the input. So those derivatives are going to be copied over. What does this look like? What does this operation look like? Downsampling, right? So the back propagation of upsampling is downsampling. Back propagation of downsampling is upsampling. But then, can I simply take a downsampling layer and use it to perform back propagation of upsampling? Anybody? Or do I have to be more careful? So Mariam, can I just use my code that I used for downsampling and use that to perform back propagation for upsampling? No, why not? Why not? Here's why. Because when I do this, I know that the derivatives of map must be the same size as the input to the upsampling layer. And so you have boundary effects. Upsampling and downsampling layers have some fuzzy way of dealing with boundaries, whether you want to introduce zeros beyond the boundary or not, whether how you deal with things at the boundaries. And so sizes, if I simply use my upsampling code and use it to perform back propagation and downsampling, I'm going to have some funky stuff happening at the boundaries, and vice versa. So although back propagation for downsampling is upsampling, and back propagation for upsampling is downsampling, these are not exactly the same operations as upsampling and downsampling when you're going forward because of what happens at the boundaries. During back propagation, we have to make sure that the derivative maps are the same size as the inputs to the operations. So here's the back propagation to the upsampling code. I've just, literally, this is just looks like a downsampling operation. Now, in your convolutional neural network, very often you're going to see convolution with a stride greater than 1. If I see convolutions with a stride greater than 1, then the size of the output is going to be smaller than the size of the input, right? Yes or no? How would you perform back propagation through a convolution with a stride greater than 1? Any ideas? Add? How would you do this? Do you think if you wanted to do this simply, exactly, if you tried to directly perform back propagation through a convolution with a downsampling of 2, stride of 2, you're going to find that that arithmetic ends up looking very ugly and your code is going to look ugly. But then it's more reasonable to think of convolution with a stride of 2 as convolution with a stride of 1 followed by downsampling by a stride of 2. And once I do this, I know exactly how to propagate derivatives backwards through the downsampling. I also know exactly how to propagate derivatives backwards through convolution with stride 1. And so I can propagate derivatives through the whole chain back to this guy. Does this make sense? This makes sense to you guys? Right. And so this is going to be much, much, much simpler because each of these two back propagation operations are really simple to understand. Whereas if you try to directly perform back propagation through this one, you're going to find it really painful. And if you look on the web for explanations on how you back propagate through convolutions with strides, you're going to find some pretty tedious explanations. But then when you realize that this is what you're performing, the whole thing becomes trivially simple. This is going to be an upsampling, and then there's a standard back propagation for convolution. Okay, so this is what you do, right? And this is going to be simpler than trying to modify backprop rules to account for stride and convolution. Now, convolution layer with a fractional stride. This was when you increased the size of the map, right? This is also part of your PyTorch toolkit, I think. How would you modify backpropagation rules to perform backpropagation through a convolution with a fractional stride? Anyone? It's going to be upsampling followed by convolution, correct? It's not convolution followed by upsampling. This is going to be upsampling followed by convolution. And once you realize that convolution with a fractional stride is the same as upsampling followed by convolution, then you can separate the operation out. We know exactly how to perform backpropagation through a convolution with stride 1. We also know exactly how to perform backpropagation through an upsampling layer. In fact, it's very simple. And then you chain these operations up. And so now the result is going to be a backpropagation from this output all the way to the input. That makes sense to everybody? Any questions? Okay. So same thing, pooling is typically performed with strides greater than 1. And this results in a shrinking of the map, which is why pooling layers were often just called downsampling layers, because you almost never perform pooling with a stride of 1. You almost always perform pooling with a stride greater than 1. But then, if you want to perform backpropagation, especially if you're performing mean pooling, with max pooling, it's not so hard because you just copy the derivatives into a single location. But with mean pooling, it becomes ugly because this effectively is convolution with a stride, right? So in this case, you can once again decompose this into 2 operations. The first is pooling with a stride 1, followed by a downsampling layer. And then of course, you can use the standard backpropagation rules for downsampling and the backpropagation rules for pooling to propagate derivatives from the output here all the way to the input. This makes sense? Questions? No? Okay. And so here's where we are. But then, as it turns out, if remember, I told you in the last class that backpropagation through convolution is often just simpler if you think of it through the lens of code. And you ask me why you would do that. Maybe that's not so efficient because you have all of this for loops. But then once you begin combining these things with stride, you can see where the code is just simpler. So here, for example, is a standard convolution. You're going to be, within each layer, you're going to be scanning left to right, top to bottom, right? And then you're looping through all of the filters. You're first computing an affine value, and then you're applying an activation to it. So this was the forward convolution, which meant that when we did the backward pass, the loops, you just reverse the order of operations. So now the loops went from the highest index down to the lowest index. And then the first thing you did was propagate the derivative back through the initial activation. And then here, in the forward pass, the affine term was always incremented by the product of W and Y. So in the backward pass, the derivative, you're going to use exactly the same location. The derivative with respect to W x prime Y prime is going to be incremented by the derivative with respect to Z x Y times Y x plus x prime minus 1, Y plus Y prime minus 1. And so you don't even have to worry about the indices. The actual indices are given to you right in this code. And so when you go back, the derivative with respect to the derivative for y at x plus x prime minus 1, y plus y prime minus 1 is going to be incremented by the product of the derivative of z at xy and the filter at x prime y prime. Similarly, the derivative with respect to the filter at x prime y prime is going to be incremented by the derivative of z at xy times y of x plus x prime minus 1, y of y prime minus 1. So do you guys see how this code is just basically literally inverting the operations of the forward pass? Right? Elvin does. What about the rest of you guys? Right? And now here's where things get simple. If I were convolving in the forward pass with a stride, how do you think this code is going to change? Anyone? If I were convolving in the forward pass with a stride, how do you think this code is going to change? Remember that when I'm convolving in the forward pass with a stride, when I'm looping through X, I'm taking a step that's one stride at a time. When I'm looping through Y, I'm taking a step that's one stride at a time, right? So you're just going to be inverting this code, that's it, using the same mechanism that we saw earlier. So when I do this over here, I'm going to be skipping forward at each time by the stride. I'm going to loop. The loop is going to step one stride step at a time. And then I'm just going to be using exactly the same code as before. So this flipping the code makes things simpler because just as you're iterating forward one stride step at a time, you're going to be iterating backward one stride step at a time. That's it. So once again, thinking of this in terms of code makes things much simpler. So also, if I were performing max pooling with a stride, typically when I'm performing max pooling, I'm stepping forward with a stride. So if I'm performing the derivatives going backwards, then I'm going to be, in fact, this becomes even simpler because when I'm going forward, I'm retaining the position. So again, what was the benefit of thinking stride? It's unlikely that you're actually going to be writing loops. If you want to, so conceptually, it makes it much simpler to decompose the operations. And in many situations, you're actually going to be doing this. I'm just presenting you two different perspectives. If all I gave you was code, you wouldn't really see what was going on. Right. So for max pooling, it's even simpler. For max pooling, remember, you're going forward in stride steps, but at each location, you're retaining the location of the maximum value and copying it over. So in the backward pass, it's so simple. All you do is copy the derivative over to the location that the maximum value is copied from. So that's about it. You don't even have to worry too much about looping back over strides because you know the exact location in the input that every output element came from. So the derivative of the max pooling layer with stride is no more difficult than the derivative of a regular max pooling layer with a stride one. For mean pooling, it's more challenging. For mean pooling, now you actually have to consider the stride. And so when you go back, it looks a little more ugly. So again, to answer you, Mariam, for convolution or mean pooling with stride, it actually makes it's conceptually and perhaps code-wise simpler to separate the operations. For max pooling, you don't really need to do it. So I'm showing you both the code and the operations for both.
Thank you.
Yeah. Any questions? Any questions, guys? Okay. So Mia, can you release this poll? Okay, 10 seconds. All right, close the poll. So is the first statement true or false, guys? Second,
True.
third. The third is false, right? Beautiful. So thank you. You guys are staying with me. And so we've shown how the derivative of the divergence with respect to every intermediate output and every free parameter filter weights can be computed. All of this can be embedded in the gradient descent framework to learn the derivatives, and those derivatives can be embedded in the optimizer, which could be simple gradient descent, stochastic gradient descent, momentum, atom, what have you, to update your network parameters. So here's the story so far. The convolutional neural network is a supervised version of a computational model of the mammalian brain. It includes convolutional layers comprising learned filters that scan the outputs of the previous layer, and pooling layers, which are also downsampling layers typically, that operate over groups of outputs from the convolutional layer to reduce the network size. The parameters of the network can be learned through regular backpropagation. Max pooling layers propagate derivatives only over the max element of each pool, as we just saw. And for other kinds of backpropagation operations, we have to be careful. And as it turns out, all of the fancy math and the operations that we saw, what they're really doing is they're ensuring that we sum over the appropriate sets of elements to account for the fact that the network is, in fact, a shared parameter network. So this last bullet, although I have not made it explicit so far, this is important. Why did we have to do all of the stuff that we did? That's because our network is, in fact, identical to scanning the input with a shared parameter network. And so when you propagate derivatives backward, we have to make sure that any derivatives computed are distributed or shared over the appropriate sets of elements that have a common value. And that's what all of these operations were doing. So is there any situation where min pooling could be useful? Honestly, I've never thought about it. So that question came out of left field. Post it on Piazza. Maybe I'll have an answer by then, or maybe one of the others in your class will. Okay. That's a nice question, honestly. Now, we just saw that CNNs are shift invariant. That was the whole entire purpose of the convolutional network. You wanted it to fire regardless of whether the flower occurred here or over here. But then there are other kinds of operations, like rotations, like here, right? Or scale, or reflection, or other kinds of transformation. How do you introduce invariance to these kinds of operations? Any ideas? Does anybody want to hazard a guess?
Maybe data augment.
Data augmentation is a good idea, but is there actually, that's a very nice idea, and that's in fact what we do. But so Chris, why do we use max pooling to decrease the size when average pooling will decrease it and preserve some information? Purely empirically. If you post this on Piazza, I will get back to that question. There is some logic behind it. But getting back to invariance, can you think of something else that you could do? Fantastic, Mariam. Exactly, right. So here's what shift invariance did. You had a filter which had represented some pattern, right? And then when you wanted position invariance, you use the same filter at the different positions at which you wanted to detect the pattern. So position invariance was used by modifying the same filter to different positions. Instead of thinking of this as scanning by the filter, you can see you can have the position of the filter as a variable. And to have the same filter trigger at different positions, you sort of transform the filter to move to a new position, right? You can do the same thing with other kinds of transformation. So for example, if I want rotation invariance, instead of just scanning with the regular filter, I can also rotate the filter itself and then scan with the rotated filter. So if I rotated the filter by 45 degrees, then this is not only going to find the pattern of the original filter, it's also going to find the pattern of the same filter if it is rotated by 45 degrees. Does this make sense to everybody? Guys, yes, no? Right. So someone said kind of. Why the kind of? Hector. Right, okay. So let me try this again, right? If I scan with this filter, let's say this filter is looking for something that looks like a petal, right? Petal that is vertical. What kinds of patterns will this filter find? If the filter is detecting vertical petal-like patterns, then what will it detect in the input? Brian. So I'll get to you. But does anybody want to answer me? If this filter looks like a vertical petal, what kinds of petals would it detect? What kinds of patterns would it detect?
Only vertical ones.
Only vertical petals, right? Now, if I rotated the filter by 45 degrees, what kind of patterns would it detect? Petals at 45 degrees, correct? It's the same petal, I just changed the rotation. So now I can use the same filter and having it detect both has introduced invariance to a rotation by 45 degrees, correct? Right. And so if I want generic transform invariance, here's what I'm going to do. For each filter, I'm going to enumerate all of the transformations that I want to permit invariance to. So if I want to permit invariance to a rotation by 45 degrees, one of the transformation is going to be rotation by 45 degrees. If I want to introduce invariance to reflection, one of the transformations is going to be a reflection of the original filter. And so from each filter, I will get all of these transform filters, one per transform, and I would be scanning using all of the transform filters. Now, clearly, this is not going to account for rotation for every angle. I choose the transformations. It's a discrete set of transformations that I'm permitting. So in this example, I permitted rotation by 45 degrees. None of these filters are going to be effective for rotation by 22.5 degrees. So we have enumerated the transforms that we want invariance to. And now each of these filters is going to be transformed through these enumerated transforms. And then you're going to be scanning with each of these guys. So now, if I were not doing this, if I were just using a regular filter, then if I scan the input with the regular filter, how many output channels would I generate? When I scan the input with a filter, how many channels do I generate? Anyone? Just one, correct? But then if I come up with 5 different variants of the filter based on 5 different transforms that I want invariance to, how many output channels would I generate? Over here. Anyone? Again, look at this picture, right? If I decide that I also want invariance to a rotation of 45 degrees and reflection, this one filter ends up being transformed into a bunch of different filters, correct? Yes or no? guys? Okay, and so if I scan using all of these transform filters, how many channels will I generate? You're going to generate as many channels as the number of transforms, right? Each, if you permit T transforms, each filter is going to generate T channels. If I have K filters and each of the K, and if I'm permitting T transforms, instead of just getting just K output channels, I'm going to get K times T output channels. That makes sense? Right. So here's the problem. We're trying to introduce transform invariance in this manner. The number of output channels can quickly blow up. So here's what your standard operation was when you're performing convolution. But then if I introduce transform invariance, for each of the filters, I'm going to go through all the enumerated transforms, transform the filter, and then scan with the transform filter. So I'm going to get as many output channels as the number of transforms, one of which is going to be the identity transform. Now, clearly, this is going to cause some problems during back propagation. How so? I know that all of these filters came from the same common filter, correct? So when I back propagate derivatives, the derivatives from all of these variants of the filter must be propagated back and aggregated in the original filter. So if I have a transform which is rotated by 45 degrees, those derivatives must be transformed back by rotating by minus 45 degrees. This is the regular filter derivatives are simply going to be passed through directly. If I have a transform which is a reflection, then the derivatives for this filter must be reflected back before being propagated here. And all of them must be aggregated to get the derivatives for this base filter. That makes sense? Yeah. So you can't capture all the orientations, just the ones that you enumerate. That's just the, yeah, Arihant. It would mean rearrangement of elements, right? So this actually ends up being very tedious. And so as a result, we never actually use a transform invariant convolutional neural network. Instead, we just augment the data and hope the network learns everything. Because if in addition to shift invariance, you also introduce transform invariance, firstly, you have to enumerate the transforms, and secondly, the computation blows up very quickly. So here's the story so far. CNNs are shift invariant neural network models for shift invariant pattern detection. They're equivalent to scanning with shared parameter MLPs with distributed representations. The parameters of the network can be learned through regular backprop. Like a regular MLP, individual layers may either increase or decrease the span of the representation by up or down sampling, and the backprop must handle this as well. The models can be easily modified to include invariance to other kinds of transforms. But this can be computationally painful, right? So far, so good. But then the model that we have so far only tells you, for instance, whether a flower was present in the picture or not. But how about the location of the flower itself? Can we get information about it? Now, if you were using a non-distributed scan, so a CNN where you didn't distribute the parameters over the various layers, then how would you, if you discover that the picture has a flower, how would you determine the location of the flower if you had a non-distributed scan? Anyone? If you had a non-distributed scan, how would you do it? You could just take we could find out which MLP is contributing most to the softmax. You could find the position of the largest input, and that's going to give you the location of the flower. That works for non-distributed CNNs. Make sense? The problem is when you have distributed scans, that logic breaks down because you really won't know at which level the flower happened, right? We don't have full control over it because trying to analyze these distributed representation CNNs and identify the size of the base pattern can be quite challenging. And so in this case, we are going to do something different. Typically, what we would do is add a regression layer. So here's your standard CNN. You would flatten the output of the final layer, and then you put it through a classification layer to get class outputs to decide if the input has a given pattern or not. But then, if I also want to find out the position of the object, then this final output layer is typically put through another regression layer, which gives you the coordinates of the bounding box within which the pattern occurs. So, okay, Murray, I'll get to your question later, right? But is this making sense? How you could find the coordinates of a bounding of the object? Anybody? Right. And this is happening. Okay, so Medha, here's the thing. We know that this final layer has information in it somewhere about the location of the flower, correct? Yes or no? So you can just put that final layer through a regression layer, which is going to be predicting 8 values. And the 8 values are the X and Y coordinates of the 4 corners of the box within which the object happens. During training, it will require labeling the data with a bounding box. Exactly. So to train this model, you're going to have to provide the bounding box information for all of the objects, and that is going to be contributing to the loss as well. So the same mechanism can also be used for instance, to predict the joints of a stick model. So those of you who have seen, well, we pulled down this demo in CMU after COVID, but there used to be a screen at the end of the corridor that connected Gates to Hellman. And when you walk down, actually, Newell Simon to Gates. And when you walk down the corridor, it would draw your skeleton on your image in real time. You'd see all of your joints and your hands and your legs and so on. It was very spooky and scary. But it was also very impressive because it actually found all of your joints. How did it do that? Using exactly the same mechanism. If I detect a person over here in this box, then I can have a regression layer which also predicts the locations of all of these joints. This can be trained using training data on which these things have been marked. And now you have a model which not only detects if there's a human being in the picture, it also finds out where their shoulder joints are, where their knee joints and hip joints are, and such like. It can draw your stick model, your skeleton, so to speak. Right? Yes. And when training, we are going to use a mix of both losses to backpropagate. So Mia, can we release the third poll? There are 3 questions here, guys. Okay. 10 seconds. All right. Can we close the poll? Do you want to answer the question? Is the first statement true or false?
True.
All three are true. Let's see if this is the case. True, true, and true, right? Fantastic. So, sorry, Kaiza-san, Zoom polls tend to be a bit of a problem. Not everybody sees them. I haven't managed to figure out why this happens in many years. But anyway, so any questions so far? Any questions? No? Okay. So we've gone through all of the basic ideas of CNNs. How is error in the bounding box back propagated to the CNN layers? So what happens here is, let me go back. This error over here is back propagated to this layer. So now this means that you have a derivative with respect to every one of these elements. And so that means the derivative maps over here are going to have derivatives coming from both this loss and this loss. Did that answer you, Arvind? Okay, so, and then the rest of it is just straightforward. So there are very many variations to this basic CNN model. You can have very deep networks, 100 or more layers in an NLP. So do these apply to when the object is found at multiple positions for both distributed and non-distributed? So, okay, first, Hector, if the training instance did not contain a flower, you would have no bounding boxes. And so that you would have no loss contribution from that instance, number one. And so it would be ignored. And second, if you have more than one instance of the object, then the model becomes a little more complicated. You're going to have to segment, you're going to have to find out all the different objects in the image. So they're using a technique called YOLO, which maybe we'll cover in one of the recitations. And then you can apply the same procedure within each of these regions to further localize the data, the class, the object. Anyway, so there are many variations to this basic model. You can have very deep. Brian, shift is one instance of a transform. It's just that if all you're using is shift invariance, then the model is simple. But if you introduce other kinds of transform invariance, then it becomes more complicated. That's all. So again, getting back to the lecture, we're going to see variations, very deep networks with 100 or more layers. The problem with deep layer networks is that the back propagation of derivatives becomes challenging. We'll see why this is the case in a few lectures from now. And so for this, we use a formalism called a ResNet. Then this other kind of convolution called depth-wise convolution, which is a somewhat different way of sharing parameters, where instead of multiple independent filters with independent parameters, we use a common layer-wise weights, and then combine the layers differently for each filter. Let's see what these things are. So I'm going to be looking at, instead of ResNets, let's first talk about the depth-wise convolutions. Now, in your conventional convolution, here's what happens. Using the cube view, this cube represents the set of all input channels to the convolution. The filter also has as many channels as the number of input channels. So when you convolve the filter with the input, this is the equivalent of convolving each channel of the filter with the corresponding channel of the input. So this operation is going to give you as many channels as the number of input channels. And then finally, all of these guys are added to give you the final output of this convolution. Is this making sense to you guys, this picture? Yes, no? Right. So basically, the filter has as many channels as the input. And so when you perform convolution, each channel of the filter is convolving the corresponding channel of the input. So the result is going to be as many channels as the number of input channels. These are collapsed to give you the final output of the filter. So if I have multiple filters, for example, if I have 3 different filters, each of these 3 filters is going to have as many channels as the input. So each of these filters is going to produce as many output channels as the number of input channels. And then for each of these filters, all of these guys are going to be summed up to give you the final output of the filter. This making sense? This picture? Right. So if the input has 10 channels, and if I have 3 filters, how many convolutions am I actually performing? Remember that each of these planes here represents one convolution, right? Again, the filter must have as many channels as the input, right? Remember, you have one component of the filter for every input channel. So if I had, if I had 10 input channels, if I had 3 filters, I am performing 30 convolutions. That is expensive. Can I reduce that? So in depth-wise convolution, here's what you do. You have a filter, just one filter, and when I convolve the filter with the input, it's going to produce as many channels as the number of input channels. But then, when I collapse them, instead of just summing all of them up, I'm going to do a weighted sum, and I'm going to use a different set of weights for each output channel. So wait, is this making sense? This visualization? Yes or no? So how do you allocate the weights? You learn those weights. Now, this is what it is. Collapsing with a weight vector is the same as convolving this as a non-distributed scan of this guy, right? It's going to be one row of weights, and that row of weights is scanning the input, and the result is going to be a single point. So this weight is going to be a vector. In fact, this collapse is like performing a single convolution with a 1x1 filter. This collapse is like performing a single convolution with a 1x1 filter. And this collapse is going to be performing, is like convolving with a single 1x1 filter. So now, if I have 10 input channels, and if I want 3 output channels, how many convolutions am I performing? Anybody? How many am I performing? Anybody want to reply to this? It's going to be 10 to get here, plus these 3. These are 1x1 convolutions, right? And so you're going to get 13 convolutions. The 10 to get here, and then these 3. As compared to the 30 that you had earlier. You see do you see how this reduces computation? Yes or no? Right. And so here's what we have. In the conventional CNN, if I have 5 filters, and if I have, say in this case, 7 input channels, each of these 5 filters is going to perform 7 convolutions, and the result is going to be 5 output channels. Here, if I want to get 5 output channels, I'm going to have a single filter with 7 channels. The single filter is going to produce 7 output channels. These 7 output channels are each going to be convolved with 5 1x1 filters to get you 5 output channels. And so, as you can see, this is going to end up, because 1x1 convolutions are very, very inexpensive, whereas these guys are much more expensive. And so this is going to end up requiring far fewer convolutions than this guy. It's also going to end up requiring far fewer parameters than this one. So when you're short on data or you're short on compute, then instead of using the standard CNN framework, using this framework, which is called depth-wise convolution, can save you both in terms of parameters and in terms of compute. Does that make sense? Yes or no? Okay. So can we? That's right. Yeah. Okay, this was an easy one, 10 seconds. All right, let's close the poll. So is the first statement true or false? And what about the second? True. And so let's see if that is the case. Yes. Filters and depth-wise convolutions do not convolve all the input channels simultaneously. And depth-wise convolutions require far fewer parameters in computation than regular convolutions. So, Tom, anytime you reduce the number of parameters, you're going to get some kind of a loss. So, given sufficient data, depth-wise convolution is always going to be inferior to regular convolution. But it's a trade-off between computation and accuracy in this case. So sorry, Kaiser, I'm not sure why you couldn't see the quiz. So here's the story so far. CNNs are shift invariant neural networks for shift invariant pattern recognition. The parameters can be learned through regular backprop. Like a regular MLP, individual layers may increase or decrease the span of the representation learned, which is what we saw. Or the model can be modified to increase invariance to other transforms. You can also make predictions related to the position and arrangement of target objects through the multitask learning. Here there were two tasks. One is classification of the object, the other is finding the location. And various variations of the basic model exist to obtain greater parameter efficiency and the better ability to compute derivatives, etc. So finally, what do the filters learn? Now, when we scan the input, each of these filters responds to some pattern in the input. Now, for the first layer, the pattern that any particular filter is looking for is simply going to be the set of weights itself. So just by inspecting the weights, you know what pattern the filter is looking for. But then when we begin getting to higher layers, remember that higher layer neurons can get complex ORing of patterns. A two-layer network can compute an XOR, which is going to fire both for 1, 0 and 0, 1. So there are many different patterns that the higher layer neurons could fire for. So what is the actual pattern that they are responding to? This must be determined on a case-by-case basis. For any given input, you would have to to determine which pattern in the input any neuron responded to, you would have to perturb the input and see if this is perturbing the output. And based on the derivatives, you must determine the pattern that it responded to, so that the receptive field for the higher level neurons must be obtained through backpropagation. And so here's some example of the kind of things that a CNN learns. This is from Hinton's original paper and AlexNet. This is a single model that has been trained to recognize different kinds of classes. And what do we see? The lowest layer neurons simply end up learning I can't see my mouse. Can I? Yeah, now I can. The lowest layer neurons simply end up learning patterns such as these. The ones at the bottom. What do they remind you of? The lowest layer neurons. What do their edges? Cortical neurons, right? So this goes back 3 lectures. It turns out that the first layer of a neural network, of a convolutional neural network, ends up responding in much the same manner as the neurons in your V1 cortex. Isn't that amazing? That we have this computational model and it seems to be learning the same kind of things that our brain does. So we're getting something right. But then as you get to higher levels, the actual pattern that they respond to depends on the input. And so when for the second level over here, some higher level, I don't know if it's exactly the second layer, when the inputs provided were faces, we find that all of these neurons are responding to parts of faces, eyes, bridges of noses, and so on. When provided with images of cars, they're responding to parts of cars. When provided with images of elephants, each of them is detecting, parts of elephants. For chairs, each of them is detecting different portions of a chair. And then when you get to even higher levels, you can see that by the time you get to the highest levels of the layers of the neuron, they actually end up responding to full face-like patterns when they're presented with faces, to full car-like patterns when they're presented with cars, full elephant-like patterns when presented with elephants, and full chair-like patterns when presented with chairs. So this is much in the same manner that we saw in the original Hubel and Wiesel paper. They showed that as you went up through the layers, you got larger and larger and more complex patterns. And that is, in fact, what even CNNs seem to be doing, which I don't know about you. I find that to be very impressive and, in fact, quite amazing that our computational model is responding in much the same manner as the brain. So you have standard convergence issues during training. So typically we use ADAM or other momentum style algorithms, tricks such as batch normalization or regularization. The number of parameters can quickly become very large, even though it's a shared parameter network. And so then you can end up with insufficient training data to train the model well. And so we'll often do things like data augmentation, where we modify the data without changing the class. So here were some examples of data augmentation. These are different objects, and they've been modified to different variants of the same object by maybe adding a little noise, or scaling them, or rotating them up by a little bit, or sharing them. And these are transformations that keep the class. So for example, this over here, I'm trying to recognize what these classes are. I'm not sure I can make out, but you can make out that in each of these examples, the class identity has not changed after the transform. So we tend to augment the data by modifying the data, right? And we use that to train the network. And so coming to the end, convolutional neural networks are now one of the most frequently used neural network formalisms. They're used everywhere, not just for image classification. They're used in speech and audio processing. In speech, we often apply convolutional networks and spectrograms. They are even used in text processing. Text is a sequence of words. We often use them to analyze the sequence of words. We use them in analyzing financial markets. We'll see that in the next class. And so, and to see how convets actually work. Back when Andrej Karpathy was a grad student at Stanford, he built a very nice demo. I believe it's still up. He did this for CIFAR 10, so you can play around with it and see what these networks actually learn. And some examples. So some examples of success. The earliest convolutional network was Jan LeCun's LeNet. Here is the architecture for it. This was in 1990 or thereabouts. But then after that, for the longest time, nobody really used convolutional neural networks because it was deemed too complex. And we never really got it to work until this paper by Hinton et al. On the ImageNet. So the ImageNet challenge was one where you had millions of images and thousands of categories, and you had to detect the category of the input. And the typical error rate was 25%. So accuracy was, the error was 25%. We would get 75% of the images right, but a quarter of the time we were wrong. Until Hinton and Co came up with AlexNet. This was in 2012. The architecture of their model was so large for their time that even the picture that they posted in the paper got cut. But then, and they provided various details for their model. And I believe this was the first time that somebody actually used ReLUs in a convolutional neural network. Previous to this, people only used sigmoids. And this was the large model for their time. It had 60 million parameters, 650,000 neurons, 630 million connections. And then during testing, just use one image. They cropped the image in many different ways, classified each of them, and voted over the entire lot. And more details over here, but eventually, when they were done, they had brought this error down from 25% to 18.2% with a single network. And if they used an ensemble of 7 networks, that error went down to 15%. And this was a huge jump in performance. And this is what brought convolutional neural networks back into prominence after many, many, many years. And once they showed this was possible, then a lot more people jumped into onto the bandwagon. So here are some of the kinds of things that they found. These are the responses of the lowest level neurons. And you see that they look like the cortical neurons. And they also showed, so here are some typical classifications. And for the first time, we were getting really remarkable classification. And even when the classification was wrong, often it was reasonable. So this picture was supposed to represent cherries, but the classifier said it was a Dalmatian. Is it wrong? I don't think so. Then also, they showed that the representation derived by the final layer of the network was meaningful. So, for example, if they presented the network with an example of a flower, use the representation that came out, and then retrieved other images with similar representations, they almost always got a flower. When they did that with elephants, they almost always got an elephant, and so on. So they showed that these representations were meaningful. And shortly thereafter, Zeiler and Fergus updated the model and reduced the error to 14.8%. This was 2013. Then VGGNet came about. These were huge networks with 140 million parameters. They ran a ton of experiments and brought the error down to 7.3%. Then Google doesn't want to be beat. They came up with Inception, which brought that down to 6.7%. And then there's ResNet. And this was the most important contribution of those times. This is where we always knew that having more and more layers in a network would improve generalization. But the performance problem was backpropagating through 100 layers was quite impossible. So these guys realized that instead of simply having layers in this manner, if you thought of each layer as learning a correction that must be applied to the input so that you're adding things back, now you could have dozens or even hundreds of layers, and derivatives could be propagated backwards reliably. And this is ResNet. And when they did that, that error, which was 25% only a couple of years earlier, was down to 3.5%. Yeah, this was ResNet details. And then DenseNet came out, and then things got really crazy. Newer architectures were coming out every day these days. I think the error rate on ImageNet is around 1%, I may be wrong, but it's a far cry from where it was when the whole thing began, right? So CNNs, you get the idea. They're beautiful models. They were originally intended for shift invariant processing of images and audio, but they could be applied for any kind of data. These days, they're used for speech, they're used for language, and you're going to see them everywhere. And in your homework, right? CNN in your homework. So I will stop here because we're out of time. I'll wait for a couple of questions, and if there are no questions, then we will end the lecture. Thank you for your time and patience. Yes.
Sorry to interruption, Professor, can you go back to the depth-wise convolution?
That's
Yeah, because I'm quite confused about for the input layer, like each channel may like focus on different part of the information of the input our input data. So I think because in the depth-wise CNN, we actually distribute our kernels in different to read different channels. So my concern is for the very beginning, the input layer, if we just because each channel have a different information of the like a local features or local information of our input data. So I feel there might be some problem.
so okay. Your question is what happens over here? So you think the patterns may actually be best determined by looking at all of the channels together, and if you're only looking at one channel, then you may get something suboptimal. Is that correct?
Yeah. Yes.
Okay, that is indeed true. And so if this is a trade-off. You get far fewer parameters and much faster computation. In exchange, you lose this. Each of the convolutions is losing something. Now, you don't actually lose it. Remember that if I just sum them up, then I'm still combining the information from all the layers, right?
Yes.
So it's just that the sheer variety of patterns that you could find in this conventional convolution, that variety is going to be reduced. But regardless, for each of these output channels, you are looking at all of the input channels, just in different ways.
I see.
Right.
So I have another question because I think for the input from the first initial convolution, I think each channel may like represent different like a local features, but after that, like each channel can actually capture the global features. So I'm thinking about whether we can just use for the initial convolution, we use the conventional CNN, and the channels after that
You
use
can combine
depth-wise.
conventional and depth-wise convolutions in any which way, right? This is just representing the computation of one layer. So there's absolutely nothing stopping you from using a conventional convolution followed by a depth-wise convolution layer, followed by a conventional convolution, for instance. Right.
Okay, thank you.
Okay, Mia, can you stop the